Catherine, if you want to pause the recording until we welcome to episode 4 of our season 5 of the lecture series. We're very excited to continue the theme of comparing what Europa Clipper is going to do at Europa to some of the exciting research that's already happening on our own ocean world. I want to turn it over to our speakers as soon as possible, but first we have a lot of activities happening, sponsored by Now coming up. So just to make sure that these are on your radar, obviously today is on your radar, April 30th, but then in May we have 3 upcoming events. We have a topical pop-up with the Planetary Society's policy experts who are going to tell us how to share our science. Best practices there. Then we have the next episode of the season 5 lecture series, which is rescheduled. And then your normally scheduled monthly steering committee meeting. We have some exciting research updates coming up then. So be sure to stick around on Wednesdays at 3 p.m. for some exciting Ocean Worlds material. All right. That's my quick pitch, as quick as possible, so that we can get into the science. Let me introduce our first speaker, Phil Christensen. Dr. Phil Christensen is a Regents Professor and the Ed and Helen Korich Professor in the School of Earth and Space Exploration at Arizona State University. His research interests focus on composition processes and physical properties of the planetary surfaces. A major component of his research is the development of spacecraft instruments, including the one we've asked him to talk about today, the Europa Clipper ETHEMIS infrared imager, of which he is the principal investigator. So Phil, I'm going to turn it over to you, and I'll be keeping a timer of about 20 minutes. I'll drop it in the chat, a little 5-minute heads up, and then we'll have a little bit of time for questions for Phil before we turn it over to Kerry. Then Kerry will have about 20 minutes to speak. We'll have few questions for her and then open it up for questions for both our speakers. So Phil, take it away.
All right. Thanks very much. And thanks everybody for joining today. As Shannon said, I'm going to be talking about the Europa Thermal Emission Imaging System, which is a cousin of an instrument we sent to Mars many, many years ago. Just a real quick little background. Shannon said, I've been doing this, but interested in exploring planets using infrared instruments for a very long time, dating back to probably when some of you weren't born. The Mars Global Surveyor instrument there at the top right, left, all the way down through the Europa Clipper instrument down there in the lower right. And one of the beauties of bunny suits is it's hard to tell that someone's getting older. But I have definitely been doing this for a while and having a great time doing it. Just these are some of the instruments we've built. As I mentioned, there's a cousin to Europa ETHEMIS called on Mars Odyssey that's been there since 2001. Is still acquiring images every day, infrared images of Mars. We've also built a number of infrared spectrometers that are interested in getting at the composition of things. But today, I'll just be talking about the Europa ETHEMIS, whose fundamental job is to look at the temperature of Europa and what can we learn from that. So just a quick reminder, there are these beautiful moons of Jupiter, Europa being one of them. They've been known about for a long time. They're gorgeous, especially with this giant, beautiful planet in the background. Just for a little bit of reminder of context, one ocean world compared to another, Europa is about the size of our moon. And as all of you know, it has an icy shell. And then what makes it interesting for today's topic is underneath that icy shell is an ocean. But it's not small. It's comparable in size to our moon. It has a very complicated history and a complicated surface. It's a very interesting object to study. Again, getting in a little bit closer, looking at the science of Europa. obviously what makes Europa so interesting is first of all, its water ice shell. But more important, even from this image taken from a distance, you can see that there are virtually no craters on the surface. It has a very young surface. I'm a geologist by background, and so that just, tells of a very interesting resurfacing recent history that's been going on Europa. And so the among the questions are, what is the nature of that resurfacing? What is the age of that resurfacing? What can we learn about studying the surface about that interior? The other thing, obviously, that you all know is that Europa has these fractures, and those fractures have long been interpreted to suggest that there is motion, convection going on in that subsurface ocean, and that motion is pulling the crust apart, allowing material to well up from the interior to fill in those gaps where the plates are separating. As I'll say more in a minute, but to jump to the chase, our job is to measure the temperature of the surface and really look to see, are there thermal anomalies associated with those fractures that can tell us about the age of when this resurfacing was occurring, when this spreading was occurring. If you look a little bit closer at some of those fractures, obviously, Europa has this amazingly complex surface. This crust is being pulled apart. In a few weeks, you'll hear from Diana Blaney. She'll be talking about the composition of some of those reddish and orangish materials, what that might be telling us about the interior. But what we're trying to do is really look at these spreading zones, these fractures, these rifts, and see, are there thermal anomalies associated with them? And if so, do those thermal anomalies vary across the moon, giving hints to the processes that are going on deep down in that ocean. Again, just another example of how this surface is being pulled apart. The very fact that we see these places where the plates are being pulled apart, material has welled up in between those plates, and how thick is that material? How old is that material? Does that material have any thermal signature? So again, just in cross-section, this is a very simplified diagram of what's obviously going to be a very complex subsurface. But the idea is that there are places where that warm ocean, water from that warm ocean is rising relatively close to the surface, and hopefully present some sort of a thermal anomaly at the surface that can be detected. Whether it's material that actually erupted onto the surface at one point and has slowly been cooling, or is it near surface water that's welling up, producing fractures, producing chaos regions. All of these things are possible, and all of them will have some type of a hopefully detectable thermal signature. And from that, can we get ideas on, the thickness of the ocean, and again, the time scale of when this upwelling has been occurring. So ETHEMIS is actually a remarkably straightforward investigation. We have two real science objectives. The first that I've been talking about is to hopefully detect and then characterize any surface thermal anomalies that will tell us about shallow water beneath this ice crust, and hopefully even evidence of recent resurfacing. The other thing we're going to do is we're going to look at the temperature variation throughout the day. From that derive a property called the thermal inertia, which is really related to particle size, porosity, block abundance, subsurface layering. It's really, what is the physical nature of the surface that's controlling how it warms during the day and cools at night. Originally, one of the primary goals there was to look for regions for future landing site assessment. Can we assess the roughness of the surface? But also we'll be looking just to understand what are the physical processes that have been affecting that surface. To go in a little more detail on this thermal inertia, these are values, thermal inertia of 50. That's very fine, fluffy material. For scale, coarse sand has a thermal inertia of about 350. Solid blocks of ice or rock have a thermal inertia of 1,000 or 2,000. So you can see those different physical properties affect how the temperature varies throughout the day. The other thing that's really take home from this figure is Europa is incredibly cold. On a good warm day, it gets slightly above the temperature of liquid nitrogen at the surface. The nighttime temperatures are around those of liquid nitrogen. So trying to do thermal measurements at those low temperatures obviously is a challenge, and it really drove the design of the ETHEMIS camera. The other thing I'll mention, many of you know that the other thing that drove our design was where Europa is embedded in this horrific radiation belt trapped by the magnetic fields of Jupiter. And so we have to fly through that belt, 40 so times on our Europa flybys. And so much of the energy of the instrument design and development actually went into trying to survive that radiation environment. So this is one of the really compelling features, models that we've put forward for why we're flying ETHEMIS. This was done by Oleg Abramov and colleagues over a decade ago, modeling what happens when ice is erupted on or near the surface of Europa. And you can see that, initially it's obviously liquid, but it cools very rapidly. And over time begins to, cool from 130 Kelvin down to sort of an equilibrium background temperature of 100 Kelvin. One of the great things about the surface being so cold is you can detect these thermal anomalies. And as I'll show in a minute, our camera, even at 70, 80 Kelvin, can detect temperature differences on the order of 1 Kelvin. And so based on Oleg's models, we should be able to, if water is erupted on the surface, sort of irregardless of its initial temperature, depth, where it came from, it will still be detectable maybe up to 1,000 years later. It'll have a few degree temperature increase from the background cold, very cold ice. So one of the things we're hoping for is that we will actually see regions on the surface where there's a 5, 10 Kelvin temperature anomaly that we can relate to recent, last 1,000 years or so, actual eruptions onto the surface. So that's one of the things we're going to do. The other one, and that I touched on, I'll say another few words, is this thermal inertia. This literally is the best available spatial thermal inertia map made by Julie Rathman et al. Over a decade ago. This is what we know about the physical properties of Europa. And the background grayscale image is actually lower resolution than what we will get from ETHEMIS. So we should be able to dramatically improve our understanding of the physical nature of the upper surface, in addition to looking for these endogenic temperature anomalies. Just to show an example that we can actually do this, as I said, we have this sister instrument called ETHEMIS in orbit around Mars. These are some much higher resolution temperature images of the Martian ice caps. But you can see, the CO2 is at about 140 Kelvin. The water is at about 200 Kelvin. And so we can clearly map ice at those temperatures. And so this gives us a lot of confidence that we'll be able to accurately and precisely map temperature distributions on the icy surface of Europa as well. And again, just to give you a sense, these are simulations of what we'll see as we do each of the flybys. Just a dramatic increase in the spatial resolution over what we currently have from infrared measurements of Europa. So even our very first scan across the moon should be spectacular. Just to see are there indeed thermal anomalies. Okay, I'll say a few words about the instrument itself. It's about the size of a fruit basket, if you will. It's a 3-mirror telescope. So light comes in through this baffle, bounces off a primary, secondary, tertiary mirror onto a state-of-the-art microbolometer array. We have 3 filters, and you can see sort of a thumb and forefinger there for scale. We have 3 filters, 7 to 14 micron, 14 to 28, and then a very long wavelength, 28 to about 70 micron filter. Again, given the very low temperatures of Europa, we need and want to get out to these very long wavelengths where the bulk of the thermal emission is occurring. We also have a calibration flag inside the instrument. One of my goals is to get very accurate temperature measurements. So we've spent a lot of time, and we will spend a lot of time on calibration to really try to, have the absolute best quality data we can. This is just sort of a exploded view of the instrument. As I mentioned, for radiation, it's sort of, think of it as a normal infrared camera in an Iron Man suit. So we have extraordinarily thick aluminum walls. We have this 5-kilogram copper tungsten shielding that goes over the focal plane, the detector. So it's this relatively small instrument that's extraordinarily heavy, simply to provide that radiation shielding. The real heart of the instrument is a truly spectacular uncooled microbolometer focal plane. These are amazing technologies. Again, the key here is uncooled, but they work remarkably well. We started with a tactical or existing device, but had to completely rebuild it, redesign it over about 5 years to get it to survive in the Europa radiation environment. But it's a truly spectacular technology advance to have this type of detector array. This is what the instrument looks like. You can see the Iron Man suit surrounding the telescopes, and then a focal plane array, the detector array there with its cover off. Again, very complex electronics that had to be completely redesigned from existing commercial devices just to be able to survive in the radiation environment. I won't say a whole lot. It's a camera. So we work in 2 modes. One is framing mode. So there's about 900 column wide image by 140 rows under each of the 3 filters. So we can take individual images with those. We also operate in a time delay integration mode where we sum at 60 hertz. We offset and sum successive images as we're flying across the surface. Very high, it's 14-bit output, so we have extraordinary resolution and dynamic range. We obviously did a huge amount of calibration here at ASU. I won't go into that, but this is a really well-calibrated imager. And then one of the key things is, how well does it do? And as you can see, these are the 3 different bands. Our requirement was 1 degree noise equivalent temperature down at 90 Kelvin. And we exceed that in the long wavelength bands. So we'll be getting images that have better than 1 degree temperature resolution at extremely low temperatures. I'll just conclude by showing a couple of images. We took it up on the roof of our building where we built it here on the ASU campus, simulated a scan across Europa. Obviously, the temperatures are warmer than they will be on Europa. But as you can see, zooming in on these infrared images, it really is going to be a spectacular imager. From 3 miles away, you could read the signs on the side of the ASU football stadium. And then just for fun, you can see bushes and trees on a mountain that's 3 miles away. And what's even fun, the temperature, you can see the water level in these water tanks based on the temperature. We're installed on the spacecraft. The spacecraft has been built. That's ETHEMIS hiding under its blankets. We obviously launched last October. Sadly, Jupiter and Europa are a long ways away, so we don't get there until 2030. So we have still a ways to go, but I'll just conclude. About a month ago, we flew by Mars for Mars Gravity Assist. We get those data down from the spacecraft in about a week or so, and these are some simulated images of what Mars will look like. So even from a very long distance, Mars will still be about 70 pixels across, and we'll use these to calibrate, improve the calibration on the 3 bands that we were observing. So this will hopefully just be a quick teaser of what we'll see in 5 more years when we get to Europa. But it'll be fun to get some data back from space of a real object, Mars, that we know really well, and that we'll be able to see how well the camera's working. So I'll stop there. I think I'm pretty close to my 20 minutes. And this is what the beauty looks like. Unfortunately, it's gone. It's on its way to Europa now. But before it left, that's what it looked like. And I'll stop there.
Awesome. Thanks so much, Phil. The test images in Arizona, that is so exciting. Very tantalizing for Europa.
Well,
Do we go ahead?
sorry. I was going to say, I mean, it really will have very nice spatial resolution. I mean, it's a remarkable advance in just infrared cameras.
Yeah. Do we have any questions for Phil before we turn it over to Kerry? He was right on time, so thank you very much. Alexi Pankin in the chat has asked, will all images be in all 3 bands?
Yes. As we fly across the surface or as we scan across the surface, we will be acquiring data in all 3 bands. So we will always have all 3.
There's another question in the chat about whether the detector requires any special calibration due to the Jovian radiation environment.
It does. Fortunately, space is a spectacularly good calibration target. It's 3 Kelvin, and we have this internal cal flag. So we do expect, unfortunately, that the performance will degrade and change over time. But we hope with those two calibration temperatures that we will be able to remove those changes and continue to get really well calibrated data throughout the entire mission. That's the plan.
All right, we have one last one from James Ray, who's very excited for ETHEMIS. Any hope of seeing compositional variations with the 3-band spectra? Do you all ever consider proposing more narrow? Did you consider proposing narrower filters for this purpose, or is Europa just too cold for that to be feasible?
All of the above, James. We did. Several groups actually did try to propose spectrometers. It is just so cold, and so we will try. We have the 3 filters. It was primarily we used those to try to get separation on the Planck curve, so we could try to puzzle out, are there temperature differences within a pixel, namely blocks and fines. So we'll try, but I'll be honest and say I think it's going to be a real challenge at those kind of temperatures. you know, you can almost count the photons one by one as they strike the camera.
Chris?
Oh, thanks you. Great talk, Phil. I hadn't seen the thing when you zoomed in on the water tanks before from the ASU picture. Do you have any feel for what the thermal resolution was? Like, what was the temperature difference of the outside of the tank with and without the water? Does that give you a clue of how well you're doing? Or was that huge compared to your 1 degree?
It was, well, it was huge compared. At room temperature, we have our noise equivalent delta temperature is about 0.05 centigrade.
Okay.
And so, you know, so that the temperature difference between the wall, you know, where the water was, you know, it was hundreds of DN, and it was probably, you know, 5 or 6 degrees. So if we flew this around the Earth, we could do some spectacular things. So yeah, it's at the Earth, it's crazy sensitive. Even at Europa, it will be pretty darn good.
So do you think you'd be able to tell like pockets of water under ice, or is that
Yeah, we think
if they're shallow?
Yeah, the modeling that we've done suggests that we can detect water down, if it's within 1 kilometer or 2 of the surface, we should be able to see a thermal signature. So that's the hope, that like on these fractures, if any of that water is even within a few kilometers, we should see it. And that's really the hope.
Thank you.
On that tantalizing note, let's thank Phil again. He'll be back at the end for the broader round of questions. But now we're going to turn our eyeballs, instead of facing out towards Jupiter, we're going to turn around and look at our own planet and hear from Dr. Kerry Cawse-Nicholson, who is a scientist at the NASA Jet Propulsion Lab in California. She is the ECOSTRESS science lead and is also involved in an upcoming NASA mission to map Earth's surface biology and geology, or SBG. Her research interests include the study of biodiversity, wildfires, and drought, as well as uncertainty quantification and the mathematical optimization of mission design. So we've asked her to come and talk about ECOSTRESS. So take it away, Kerry.
Thank you so much, Shannon. Thank you for having me today. And thanks, Phil, for a great talk. I learned a lot about Europa today. And here at JPL, I was actually able to check in on Clipper as it was being built in our clean room, which is just one building down from me, which was an exciting experience. And so I loved the lead in to what you said about being able to measure the temperature of Earth, which is exactly what we're doing with ECOSTRESS. And so this is ECOSTRESS as it is being plugged into the Japanese external facility on the International Space Station. And so you can actually see the robotic arm has grabbed it from the trunk of the Falcon 9 rocket and is pulling it across to the side of the space station, plugging it in like a giant thumb drive. ECOSTRESS, it doesn't have nearly the same constraints as ETHEMIS had, obviously. And so this is about the size of your refrigerator. It's really big, it's really heavy. We are conveniently plugged into this giant power bank that is the ISS. And so this instrument, it's not a microbolometer, it's a mercury cadmium telluride detector array with it's cryocooled with 2 cryocoolers. And there are 2 onboard black bodies for calibration. And so here posed on in its position on the ISS, looking down at Earth, ECOSTRESS was originally designed to study ecosystems, particularly how plants respond to changing water conditions, how the temperature variations impact vegetation growth, how this may impact agricultural yield and maximize agricultural water use. And the way we get to these goals is really by measuring temperature. So vegetation, on the underside of their leaves, they have these tiny pores called stomata, and they open those stomata as part of the photosynthesis process. And as they do so, a small amount of water escapes, and this is transpiration. And so one of the products that we produce from ECOSTRESS is called evapotranspiration. It's the sum of the evaporation from the exposed surfaces of the plants and from the ground, in addition to the transpiration from the plant itself. Now, some plants, when they're stressed and they need to preserve water, they close their stomata, and this causes them to heat up slightly. And that slight temperature change is what we detect from ECOSTRESS. And so here I'm showing an image of ECOSTRESS that's been processed to evapotranspiration, where the blue represents a lot of transpiration. Those plants are transpiring, they're happy, in many cases because they're irrigated, because this is an agricultural area. So these circles are pivot irrigation circles. And this beige area in the background shows areas that have not been irrigated. And so there is very little vegetation there. Where there is vegetation, that vegetation is stressed, it's not doing so well. And the reason you might look to evapotranspiration, or ET for short, is because you start to see that drop in ET several weeks before the plant actually turns brown. And so this is an early warning system. And one of the ways that we can use this is to inform irrigation. And so if a farmer was to see that the field was starting to experience these, say, these lighter blue colors, then that fields could probably do with a little bit more water. Conversely, some farmers have historically farmed by flooding the field with water for certain crops like rice. And now that in many places that water is being very carefully monitored and you have to pay for your water use, perhaps you don't want to use more water than you really need to. And so with that in mind, there are several private companies that have actually been using your ECOSTRESS and other data sets in apps that provide agricultural water users with notifications on how to maximize water use for irrigation. This is an example from a company called Land IQ, which provides irrigation advisories in the Central Valley of California. And here they're particularly interested in providing information to groundwater sustainability agencies and irrigation districts. And so once again, how can we preserve our limited water resource while still maximizing agricultural yield? Now, because our base measurement is temperature, of course, we can measure more than just the temperature of plants. And one area that has been of great interest is measuring the temperature of cities. And so this is an image, an ECOSTRESS temperature map over Los Angeles. And so I live just to the northeast of this image. And you can see that we have cooler areas along the coast, as you might expect. You can see the San Fernando Valley is extremely hot. You can even see the remnants of the burn scars from the severe fires that we had around this area in January. And you may notice that you can see the grid of the streets. So the streets tend to retain that heat much more than surrounding areas. And it's particularly true in the San Fernando Valley. And so these images have helped to inform some urban design decisions. And so we've been working with the city of Los Angeles as they've been experimenting with urban cooling. One of the efforts that they've tried is to paint the streets with this particular paint that reflects the solar energy away. It prevents it from being absorbed into the street and retained, radiating that heat out overnight. And so they tested this out in San Fernando Valley, and it has been so successful that they are now beginning to expand this project throughout Los Angeles, and they've even now painted hundreds of miles of road in Phoenix with the same technology. So this is important because urban heat is actually an incredible health risk. It's not well known that heat waves are the deadliest natural disaster we have here on Earth. More people die each year from heat exposure than from earthquakes, tsunamis, hurricanes, etc. So that was all just to provide some context, but here we're interested in oceans. And so if I zoom into an image around Los Angeles and rescale it slightly, now we're looking at the Channel Islands off the coast of California. And those temperature changes that you're seeing in the blues and the yellows are really showing you the eddies and the currents in the water here. So that large island on the right-hand side that looks like an upside-down dolphin, that's the island of Santa Cruz, part of the Channel Islands. And I was camping there just a couple of weeks ago, which is a great experience if you ever have the chance to go there. And this is a really ecologically interesting area because you have the cold currents from the north mixing with the warm currents from the south. And that creates a lot of upwelling, which provides nutrients that are available to a lot of the sea life that live in this area. And so being able to use these temperature measurements over the ocean can be important for many applications, particularly because each ECOSTRESS pixel being designed to study agricultural fields is about 70 meters. So that's about 3/4 of the size of a football or a soccer field. And we can use this to explore things like marine heat waves. So this is an example in Florida in 2023. And so here on the left, you can see the warning that was put out by NOAA, where the variable that they're displaying is degree heating weeks. And so this is as soon as the water reaches a temperature where it's a threat to for coral bleaching, they start recording temperature accumulation. And so here you can see those gray fine lines that shows what that degree heating week metric has looked like in previous years. And you can see that 2023 just far exceeds what they had seen previously. And so now there's risk of severe widespread bleaching mortality. And so the left is the reanalysis image that NOAA put out showing those high temperatures just to the south and around the Florida Keys. And on the right, you can see that same area studied with ECOSTRESS with those very fine resolution pixels. And so suddenly you can pick out with much more detail areas that are at risk. If I move to another paper that came out looking at the Red Sea near Saudi Arabia, similarly, they were looking at how ECOSTRESS water temperature compares to what's currently the best available measure, which is produced by this GRIST project. This is high resolution sea surface temperature. It combines different satellites to produce a 1 kilometer highly accurate measure of sea surface temperature. And so what you're seeing in that image on the bottom left is the variance in water temperatures that the coral are exposed to. So coral reefs, in a similar way to the frog in the pot analogy, if they're exposed to gradually increasing temperatures, they tend to be okay. But if they're exposed to a very sudden and very rapid change in temperature, that's when we start to see coral bleaching and die off. And the image on the right is looking at the same area using ECOSTRESS. And I want you to note the difference in color bars between the bottom and the top. So the top, the variance reaches 25 degrees Celsius, whereas at the Celsius squared, whereas at the bottom it's only 5. And suddenly you can start to see these areas, especially around islands and near the coast, where some of the typical sea surface temperatures are not available due to the land masking. And you can now find very, very fine scale estimates of where reefs are at risk. So these are important not only for reef health, but also for fisheries and other products that may support local economies. So for example, this study looked at ECOSTRESS temperature off the coast of Spain. And here they're looking at shellfish, farmed shellfish, and how they respond to these marine heat waves. And something that they discovered, which I thought was really interesting, was that the clams that grow in and amongst seagrass, and so that's that image on the top left, that inset, they are much more resistant to the impacts of the heat waves. So the water heats up, the vegetation absorbs some of that water, or even prevents the circulation of that very warm water right down to the seabed. And those clams were much more likely to survive. And so now suddenly we have a strategy. And so we have researchers that are working with local fisheries in Spain to implement some of these potential mitigations so that they can continue to create produce in the face of water temperatures that are changing. Now, sort of moving to more of a conservation focus, we're moving to the San Francisco estuary. And so this is on the west coast of California. And one of the animals that live here is this fish, the Delta smelt, shown in the top right. It's an endangered species, and it lives in the Delta and the San Francisco estuary. And this water is obviously very important to the region in terms of providing water for local use, water for agriculture, and it's very carefully managed. One of the impacts is that being able to carefully control the flow of water throughout the estuary means that some of the smaller water flows then heat up, and the Delta smelt is not able to survive when the water exceeds a certain temperature. And so on the left, you can see a map of the water temperature of the estuary that ECOSTRESS produced. And once again, you can see the importance of that high spatial resolution in actually being able to make out those smaller water flows. And on the right, you can see a suitability map for where these fish can still survive. And you can see that a lot of the smaller water flows are black. That means the fish is not able to survive there any longer. And so this is of great concern for conservationists in the area. And our team has been partnering with resource managers in the area to support water operations that may be more beneficial to restoration of this environment. And we can also look beyond just the temperature of the water. There are impacts for water quality. And so this is another image of California after the Woolsey fire. You can see that image on the right, that a lot of vegetation was impacted in the Malibu Creek watershed, outlined in blue, where the Woolsey fire extent is in red. And you can see that a lot of that water flows directly out into the ocean. So you can imagine that a lot of the vegetation has burned away. There's now exposed soil that can erode much more easily. In some cases, there's some agricultural areas. And so everything in that soil is now washed down into the ocean. And so the figure in the middle is showing ET as a proxy for vegetation content in blue. So you can see that sudden drop after the Woolsey fire, where that blue figure, the ET drops as the vegetation is burnt away. What happened after that is that there was a lot of precipitation. So that's that line in orange. So there was the fire, the vegetation had burnt away, there was rain. That suddenly washed everything down. And this study looked at the impact to various water quality indices. And one of the ones that's especially horrifying is that the fecal index really skyrocketed after this event because of what was washed into the ocean. And so since I've seen this, I have not been swimming off the coast of California, but nevertheless, it speaks to our ability to monitor the environmental impacts to water following fire. Beyond the water itself, the water obviously also supports many ecosystems, especially mangroves. And so that image to the left is showing vegetation stretch in in a World Heritage Site in Southern Asia. But the study that I've referenced here was looking at mangroves throughout the world. So we're interested in mangrove forests because they take up a lot of carbon and they tend to be very efficient. And so water use efficiency is the ratio between carbon uptake to water used. And so where water used, we use evapotranspiration as the proxy. So this study found that mangroves had a water use efficiency twice that of evergreen broadleaf forests. And that's that figure to the right, where the blue dot is about twice as high as the red dot. So that means that when mangroves are under greater water stress. They're still able to take up a lot of carbon, unlike forests, which may be less productive in the face of drought. However, that graph to the left shows sensitivity to precipitation. And so what that means is that once the water retreats, then the mangroves are obviously going to be significantly more impacted in terms of die-off. And so once we reach a certain point of lack of water availability, we may lose this resource that is able to very efficiently take up a lot of carbon. So these are just some examples that I hope to give you, showing some applications of where we use ECOSTRESS to measure water temperatures on Earth and how this can impact agriculture, ecosystems, and just better understanding our environment. So I'm going to stop sharing, and I see some questions in the chat.
Yes, let's all thank Kerry.
Thanks.
That was such a whirlwind tour of some of the fascinating science that EcoStress is enabling. Thank you. We'll kick it off with one of the chat questions. Adrian asks, with such accurate temperature resolution, does this provide a better El Nino and La Nina event prediction?
So we typically don't use EcoStress for climate predictions because so there's both a positive and a negative to being on the International Space Station. And so the positive is that because of its precessing orbit, it means every time it comes over at a different time of day. And so that gives us really exciting insight into diurnal water use from plants. But because we're not that consistent measuring temperature at the same time every day, it becomes more difficult to construct time series. And so we typically use the polar orbiters for looking at longer term trends like El Nino and La Nina. But I certainly think that once you have a better picture of what's happening, zooming in to the area of heating water with EcoStress will give you a better feel for what's happening at finer spatial resolution.
Chris?
Thank you. That was an amazing tour de force, Kerry. We covered a lot of ground. So apologies if you did say it, but in the plot that you showed of showing the surface currents around the islands in the Channel Islands, what was the dynamic range in temperature there that you were pulling out?
Oh yeah, I should have put in a color bar, shouldn't I? Sorry. It was about 5 degrees Celsius. And
the whole range of, wow. So there's a lot of structure inside that 5 degrees
yes,
you're pulling
exactly.
out.
Yeah, which is really amazing.
Wow.
And
Okay.
how deep into the water is that?
We typically only measure the very, very surface of the water, so what we call skin temperature. So our penetration is not very, very deep.
So does that mean you also have a handle on how much the roads are cooler in Los Angeles that have been painted?
Yes, we do. And I decided to focus on water here, but I do have other slides in hand that showed the temperature impact to the streets. And I think it was about 10 degrees Fahrenheit difference in the painted versus the sort of more standard streets, which had a significant impact because that 10-degree difference was at an EcoStress 70-meter pixel. So that's much wider than just the road. So that's the impact to the whole neighborhood.
That's a very hopeful little tidbit to end the Kerry only questions section. So now we'll open it up to questions for both Kerry and Phil. I'm going to take host's prerogative to pull on something that you both kind of talked about. Kerry, you were talking, you gave us a great run through of a variety of different ways that these data, which is so fascinating that it's like just temperature, right? But then all of these other properties are being pulled out from just temperature, and how that's being used to feed into actions by farmers or research managers. So I was hoping that Kerry, you could talk a little bit about the timeline of that kind of interaction in terms of like when the data is collected, when it's processed, and like when, you know, somebody gets to use that. And then Phil, I was hoping that you could similarly talk about whether ETHEMIS data, whether there are plans for ETHEMIS data to be processed and analyzed in such a way to feed into Clipper operations in real time.
Yeah, great question, Shannon. So data latency is really a key variable of interest for a lot of our application users, as you said. So typically we get the data. Our first product that we produce is Radiance, that sensor, as you might expect. And so that data is available to the public after about 6 hours after acquisition. And to transform that to land surface temperature, we need some of the meteorological reanalysis data to understand the atmospheric conditions. And so that's typically available within about 24 hours. And so our power users are able to take the 6-hour data and turn it into their own data products.
Awesome, thanks.
Our timeline isn't quite that quick. It takes almost that long just to get the data back from Jupiter. But we are doing the same thing. So Clipper will be in a 2 to 3 week orbit. And so we'll get the data on the ground within a day, process them, and within 24 hours or less, they will be available to the science team to help with the planning. So the whole idea is, can we find thermal hotspots that then either the camera or the near-IR spectrometer might image on a subsequent orbit, especially if we see any signs of dynamic changes going on the surface. So yes, we will definitely be using these data to feed into real-time operations of the mission.
Thank you both. Any other questions from the audience? I think I don't see any hands, but I could just be incompetent in hand identification. All right, in that case, I'm going to continue to take my prerogative. Phil, when ETHEMIS is you know, taking these observations that then might be acted upon in the subsequent orbits, are you also taking data concurrently with the camera and the spectrometer? Like, do you have overlapping footprints already, and then it's just a matter of following up?
Unfortunately, we don't quite. The camera is on a 2-axis gimbal, so it can look wherever it wants. We just are foresighted with the spacecraft, so we look straight down all the time. So to that extent, they can look off to the side and do a lot of other things. But we will be on continuously. We'll get a noodle underneath the spacecraft, so we will have sort of a continuous coverage. Hopefully, there will be quite a bit of overlap between all 3 instruments, because that's really what you want, the full wavelength range. One of the things I didn't really say, from our standoff, we'll do a scan. We have about 3 kilometers per pixel, and then as we get closer, we'll cover a lot of Europa throughout the mission. We hope to cover all of Europa at about 500 meters per pixel, something like that. So eventually, we'll be looking at the same places the cameras do, but it will take a little bit of coordination to look at the same place at the same time.
If we could only all be mounted on a gimbal, huh?
Yep.
Brooke, I see you've got a hand raised. Go ahead.
Sorry, I was trying to figure out how to raise my hand. I was like, if I show my face, that's enough.
That's
Great talks by both of you. Harry, I had a question for you. Since I'm not familiar with your literature and tracking ECOSTRESS in general, I figured you might know. Has anybody been tracking the occurrences of harmful algal blooms along coastlines and trying to, use ECOSTRESS for either predictions or monitoring or tracking the location of them?
Yeah, great question. And of course, harmful algal blooms are often driven precisely by increased water temperatures. And so there is some ongoing research, especially in collaboration with PACE, which is a spectrometer looking specifically at oceans. And so nothing has been published on that just yet, but it is an area of active research.
All right. Well, this has been a fantastic pair of talks. Thank you, Phil and Kerry, so much for coming to speak with us. The point of this lecture series really is to provide a better understanding of our companion ocean worlds, Europa and the Earth, and I think you two have done that quite well. So let's thank our speakers again.
Thanks so much for
And-
having me. It was great.
Absolutely. And we'll call it a day.
All right. Thanks, everyone.
Thank you.